this first example, we have secant squared minus 1 over secant squared. The goal is to prove, show, verify, without crossing the equal sign, that it breaks down to be the sine squared. So essentially, that's your answer. The answer is supposed to be sine squared. How can we take the left side and try and use the identities to break it down? So secant squared minus 1 over secant squared. What can we do to get it broken down, Emily?
Well, secant squared minus 1 would equal tangent squared.
Yeah, so that's the identity that involves that 1 plus tangent squared equals secant squared. So secant squared minus 1 can change to the tangent squared. And I am not going to write that sine squared every single time. I'm just going to kind of leave it over there. So that's the Pythagorean identity. We still have to continue to use another identity. So what else can we use? Emily?
Secant squared equals 1 over cosine squared.
Let's see. So secant squared is the same thing as 1 over cosine squared. That's that reciprocal identity. And Emily, if you have 1 over something, that means what?
You multiply by the numerator.
Right. So whenever you have 1 over something, when you are dividing by a fraction, that fraction flips to the reciprocal, and really you're multiplying the numerator by that fraction. So cosine squared is now in the numerator times the tangent squared. So 1 divided by the cosine squared really means you're taking the reciprocal of this and placing that in the numerator, because when you're dividing by a fraction, you're multiplying by the reciprocal. Great, what else can you do?
We know, based on the quotient identity, you know that the tan squared theta equals sine squared theta over cosine squared theta. So we can multiply it by cosine squared theta and the cosine squared theta.
And then our cosines cancel, and we end up getting sine squared. Which, if you look back to what we were trying to get it equal, all the way at the top, here's my sine squared. And now we've verified, proven, shown, whichever words you like best, that it can be broken down, simplified to the sine squared. Emily?
Can you expand the sine squared from the beginning to try and equal the left side?
Yes, you could have done that as well. So you can choose a side at this point and pick a side that you like best, because sometimes you might see something on the left that works, sometimes you see something on the right. But whatever side you choose, you have to stick with. So you can't go back and forth from one side to the other. So if you want to work with the sine squared and trying to get it to equal the other side, that's fine, but you have to continue just to work with that side. You can't do like half on the one side, half on the other. Other questions? So if you look at the second one right underneath it, we have tangent plus cotangent. We're trying to get that to be secant times cosecant. So as Emily said, can you start with the other side? Sure, you can start with either side at this point, but you have to pick a side and try and get it to equal the other side. And it kind of depends on what you see when you're looking at the problem. And again, our goal is to get secant and cosecant. So like think about the identities that we could use to try and help us get secant and cosecant. Grant, what do you think?
Well, I see that cotangent is the, I guess it would be reciprocal of a tangent.
Okay. So he said the cotangent could be the reciprocal of the tangent. So we could make that,
So it would be tan plus 1 over tan.
Emerson? So, did anybody do this? Jake, what'd you do?
I turned tangent and cotangent into sine x over cosine x plus cosine x over sine x.
Okay. So, Grant, did you work through it from this stuff?
No.
No, okay. So using the reciprocal identity sometimes works, but sometimes it doesn't really get us anywhere. And so you try an identity and it might not be the correct identity, and if you can't get anywhere with it, then try a different identity. So instead of using the identity to make it the reciprocal, because they don't cancel since it's an addition sign, let's see if there's maybe a different identity that we can use. So going back again, starting over, because that's what you're going to have to do with some of these problems. You try something, you're going to have to start over. So Jacob said another option would be to use the quotient identity. So this could become sine over cosine, and cotangent could be cosine over sine. And again, I will never write the other side. Like, I know that's the answer, but I'm not going to repeat it every single time. So after you choose a different identity, then you have to think to yourself, like, all right, how does this identity help you? There's an addition sign there. So what would you need to do to work through the problem, Sean?
Found my common denominator.
So adding fractions means we need to get a common denominator. Sean, what would the common denominator be?
Cosine x times sine x.
So the left side times cosine, the right side times sine. So now what do you have?
I have
Hold on. Let's start that over. How about the left side times
Yeah,
sine?
that looks
Sean's
like-
like, what are you doing over here? And the right side times cosine. That's better, right, Sean?
yeah,
Okay. So then what do you have on the top, Sean?
sine squared x plus cosine squared x.
Right. So now the top, you have a sine squared and a cosine squared. The bottom is now multiplication of sine times cosine. And the identity, Sean, that we can use with sine squared plus cosine squared is equal to 1, yeah. So there's that Pythagorean identity. They get used in most of the problems. So Sean, what is 1 over the sine?
1 over the sine is equal to cosecant x.
And 1 over the cosine
Secant x.
is equal to the secant x, which is the exact same thing with multiplication as the secant times the cosine. So you changed addition into multiplication by using common denominators, because now the denominator is being multiplied. The numerator became 1, and 1 over both of those, that's that reciprocal identity. Questions? So flipping, looking at number 3. This is definitely a problem where you could choose a side and easily, either way, kind of work through one or the other. So choose a side that you want to start with, whichever one you see. And you think, I can do something with this problem because I noticed that this is in the denominator, or I noticed that this is in the problem. So pick a side and see if you can try and change it to equal the other side. Verify the left is equal to the right, or you like the right side, so see if you can get that equal to the left side. Grant?
In order for Pythagorean identities to work, do they have to be squared?
Yes, yes. So the Pythagorean identity is just like the Pythagorean theorem. The terms have to be squared in order for you to use the Pythagorean identity. Anybody starting with the right side? I think the right side for this one might be a little easier to look at. To start with, you did the right side too. Both of them work. Do you do the right side?
Did the
That's last time.
and then I did the right side.
For that
Guessing
one.
I'm trying to do it
For the other side too.
crazy.
Yeah. So Emerson, if you start on the right side, what did you do or notice on the right side that you could start with the problem?
Well, I tried to get a Pythagorean identity, so I multiplied by 1 plus sine y over 1 plus sine.
Yeah. So in the denominator, if this problem was given to us in the last section, we would use that conjugate information and multiply the denominator by its conjugate. Because the hope is that you can then use the Pythagorean identity. So Grant asked, does it have to be squared? Yes, it does have to be squared, but we can try and make it square by using the conjugate. So the top part, we have, did you distribute, Emerson, or keep it out?
I distributed.
So top part says cosine y plus cosine times sine. And Emerson, the bottom becomes,
1 minus sine squared.
right, 1 minus sine squared with a y. So the identity that you can use then, Emerson, with the Pythagorean identity changes the denominator into what?
Cosine squared.
Cosine squared. So the whole goal of using the conjugate is so that you can get the denominator to change with one of those Pythagorean identities. Alright, so we went from a denominator that had a subtraction sign to now just a cosine squared in the denominator. So that's good because we went from at least 2 terms to 1 term. What can you do with it at this point? Jacob?
Factor of cosine.
So he said you could factor out a cosine. So we can take this cosine and pull it back out. That leaves us with 1 plus sine. And Jacob, what happens when you factor out that cosine?
It cancels.
So if we pull that cosine out, because they both have cosine in common, then the cosine on the top cancels, leaving us with 1 cosine on the bottom instead of it being cosine squared. So now on the top we just have 1 plus sine, and on the bottom we only have a cosine. So we went from cosine squared, but now we just have cosine. But it's still not quite where we want it to be, right? How do we get it there?
So if you separate the fraction, it's 1 over cosine y plus sine y over cosine y.
Right. When you have a common denominator, you can take that common denominator and split the numerator up with each piece of the denominator. So 1 over cosine plus sine over cosine. So 1 term in the denominator, that's our common denominator, the numerator can separate. And then that gives you the secant plus the tangent. If you started on the left side and worked your way to the right, so you would change this to 1 over cosine, you change that to sine over cosine. It is the exact same process, it's just the reverse. So notice my answer is sine plus tangent. So if you use the other side, essentially you're going to work yourself up and kind of go through the exact opposite way. You're still using the conjugate fact, you're still going to have to multiply by the conjugate, but you're multiplying by the conjugate of the numerator instead of the conjugate of the denominator. So if you started on the left side, did anybody get on the left side and get to work? So you can start on the left and work yourself down to the right, but you have to still use the conjugate fact. So anytime you have that 1 plus something using the conjugate, whether it's in the numerator or the denominator, it is usually the best bet for you to take, because that gets the identity. All right, so one more crazy problem with powers. We have sine cubed, cosine to the 4th, and then on the right side, it's cosine to the 4th minus cosine to the 6th in parentheses, and then the sine on the outside. So again, just looking, is there something you see in the problem on either side? Emma?
On the right side, the 2 cosines have a common, they both share a cosine to the 4th.
Right, so greatest common factor, if that was x to the 4th minus x to the 6th, you can factor out what they have in common. So Emma, you said take out a cosine to the 4th. What does that leave you with then?
1 minus cosine squared.
Right, 1 minus cosine squared x. So factoring is kind of something to notice when they have terms in common. So large powers of cosine, both cosines, you can't actually subtract them, but you can factor something out. After you factor that out, what else could you do then?
1 minus cosine squared x in parentheses can become sine squared.
Right, so that's that Pythagorean identity. 1 minus cosine squared is really sine squared. And then one last step, Emma. Yeah, these guys here, you have 2 of them and another one, so it's like having an x squared and an x. They get multiplied together, and that gives us the sine cubed, and then the cosine to the 4th that we factored out. So we verified by using factor. Anybody use the left side? I know, Jesse, you were trying. So to use the left side, if you pull this apart and just separate it, saying you have a sine times a sine squared, and then the cosine to the 4th. Kind of working the opposite way. This would change with the identity 1 minus cosine squared with the cosine to the 4th, and then you would distribute that through. But that sine cubed, you can just break that apart and kind of do it like it's the opposite. So when you're working with both sides, they kind of like eventually meet in the middle in a way, working through one side to the other. So homework tonight, 1 through 8 are just basic identities, getting you to kind of get those identities in your brain. 11 through 20, they're all of those problems, not the even, not the odd, because you know what the answer is. The answers aren't in the back of the book, you already know what the answer is. 21, 23, 27, 2 equations there. Plug those equations equal to each other and show that the left is equal to the right. Anybody like to do 17 or 20? Emerson, I think you got 2 already.
Got
I know, right? Emma, you'll try 17? Okay. 20? You'll try 20, Elena? Thank you.
If I'm not going to be here Thursday,